All right, let's jump straight into this explainer. We recently got a viewer request that simply said, "Teach me mass spectroscopy." And I gotta say, it is an absolutely fascinating subject. It's this incredible analytical tool that elegantly bridges physics, chemistry, biology, and even deep space exploration. Basically, it's a technology that literally weighs the atomic makeup of the universe. And today, we're gonna unpack exactly how it all works. Now, to the untrained eye, this machine can definitely seem like dark magic, or, some mysterious black box. The author of our source text, Jürgen H. Gross, actually hit the nail on the head when he noted that people outside the field often talk about it as if it's straight out of an Edgar Allan Poe mystery, just full of shadows and arcane secrets. But honestly, there is no magic here. Just brilliant, highly understandable science. So today, we are going to dispel all those rumors and break this complex machine down into pieces that make perfect, logical sense. So here's our roadmap for today. We'll start with the core principle, then explore the anatomy of the machine, learn how to read the data, and finally, look at the infinite scale of this technology.
Okay, part 1. The core principle. Understanding the basics.
Actually, before we go any further, I do have to make a very gentle correction to that initial viewer prompt we received. The 0th law of this field, and the experts are pretty strict about this, is that it is mass spectrometry, never mass spectroscopy. Why the distinction? Well, because unlike spectroscopy, which measures the absorption or emission of light, this method doesn't rely on light at all. We aren't looking at photons. Instead, we are physically separating and detecting isolated gas phase ions based entirely on their mass and their charge. And that fundamental difference brilliantly illustrates why this tech is such a game changer. Because we are quite literally weighing molecules, the applications are just practically endless. It's an indispensable tool for identifying unknown forensic substances at crime scenes, sequencing incredibly complex biomolecules in medical research, and analyzing the intricate, messy makeup of crude oils. The technology has even been miniaturized for space missions so we can analyze extraterrestrial atmospheres. It essentially gives us the precise molecular recipe of, well, almost anything.
Moving right along to part 2, anatomy of the machine, inside the black box. Let's actually step inside.
What's really cool is that every single mass spectrometer out there, no matter how wild or complicated it looks on the outside, follows one exact logical sequence. We always start at the sample inlet, move into the ion source, pass into the mass analyzer, and finally end up at the detector. There's also this absolutely critical transition from standard atmospheric pressure down into an ultra-high vacuum, all of which is heavily controlled by the data system.
So think of the machine as a highly specialized chemical laboratory built specifically for gas phase ions. It executes 4 distinct steps. First, it introduces the sample. Second, the ion source transforms those neutral sample molecules into charged particles, which is crucial because the rest of the machine can only handle charged species. Third, the mass analyzer sorts these newly formed ions. And fourth, the detector actually counts them up. But there is a massive catch to all of this. This whole process of separation and detection, it absolutely must happen in a high or ultra-high vacuum. We're talking about incredibly low pressures here, around 10 to the minus 5 to 10 to the minus 9 millibars. To put that into perspective, if the machine were just full of normal atmospheric air, our delicate, tiny sample ions would constantly be crashing into background gas molecules. Their paths would get completely altered, they'd lose their kinetic energy, and they would simply never reach the detector. The vacuum basically clears the highway so the ions can fly unimpeded. Let's zoom in on step 2 for a second, the ion source. When the sample first enters, we actually have a choice in how we charge it. We can use hard ionization, like electron ionization. This method aggressively shoots energetic electrons at the sample, literally shattering the molecule to reveal its underlying puzzle pieces, which gives us great structural clues. Or, alternatively, we can use soft ionization, like electrospray ionization. This gently imparts a charge to the molecule, keeping large, fragile biomolecules perfectly intact, so we can weigh the whole thing at once. Once they're ionized, the molecules are accelerated right into the mass analyzer. In a classic magnetic sector analyzer, for example, as the ions fly through the magnetic field, they experience something called the Lorentz force, which bends their trajectory into a curve. Think of it like cars taking a sharp turn on a highway. Their momentum determines how sharply they curve. Heavier ions are harder to turn, so they drift into a wider path, while lighter ions are whipped into much tighter curves. By tweaking the magnetic field, we can precisely control which specific mass makes it all the way to the detector slit.
As these sorted ions successfully strike the detector, the fundamental metric we're recording is their m/z, or mass-to-charge ratio. And it is super important to understand that the machine doesn't just measure pure mass, it measures mass divided by charge. So if an ion has a single charge, the m/z value equals its atomic mass. But if an ion happens to carry a double charge, it'll show up at exactly half its actual mass value on our scale. This m/z ratio really is the absolute bedrock of all the data we collect.
All right, part 3, reading the data, decoding a mass spectrum.
When you look at a classic mass spectrum, you'll typically see that m/z ratio we just talked about plotted against relative intensity. That intensity reflects the abundance of ions hitting the detector at that specific m/z. The tallest peak toward the higher end is usually our intact molecular ion, and those smaller peaks trailing off, those are the fragment ion peaks. Remember that hard ionization we discussed earlier? Well, this shows exactly how the original molecule shattered into smaller, measurable pieces inside the machine.
Now you might be wondering about the vertical scale on these charts. Notice how the absolute tallest line in the entire spectrum is always set to exactly 100%? Why do we normalize the data this way, instead of just showing the raw actual number of ions we detected?
Well, that tallest line is what we call the base peak. We artificially set its intensity to 100% and then scale all the other fragment peaks relative to it. We do this because the raw number of ions depends heavily on how much sample you happen to put in, or even just the specific quirks of the detector on that particular day. By normalizing the base peak, a scientist in Tokyo can easily and accurately compare their spectrum to one generated by a completely different machine in New York. It essentially creates a universal visual fingerprint for the molecule.
And finally, part 4, the infinite scale, from origins to the future.
Believe it or not, this entire scientific field kicked off over a century ago with the physicist J.J. Thomson. While his face is now engraved on prestigious international medals, his very first mass spectra were literally just glowing parabolic branches on a fluorescent screen. Scientists used to have to physically measure those glowing arcs with a ruler just to calculate the mass. It is quite a far cry from the instant digital readouts we rely on today, but the core principles, they remain exactly the same.
And man, we have come an incredibly long way from those tabletop glass tubes. Today, the technology has evolved into massive, room-sized installations. Take an accelerator mass spectrometer, for example. In these giant facilities, ions are accelerated to incredibly high kinetic energies, using equipment originally designed for particle physics. This allows researchers to detect trace radioactive isotopes with just mind-bending precision, unlocking massive breakthroughs in things like radiocarbon dating and geology.
So we've seen how mass spectrometry is this highly structured, profoundly logical tool that successfully bridges the gap between extremes. I mean, it can be small enough to ride along on a Mars rover or large enough to fill an entire warehouse, gentle enough to weigh a living biological cell perfectly intact, or forceful enough to completely shatter an oil molecule to reveal its underlying secrets. As this technology just continues to evolve, you really have to wonder, what invisible chemical mysteries will it solve for us next? Thanks so much for joining me on this explainer, and definitely keep asking those great questions.